Okay, folks, welcome to the first video in our flipped classroom experiment. We're going to be starting on section 7.1, which begins on page 417. And what we're talking about today is trig functions of real numbers. All right. There's plenty of stuff in this particular section that we have dealt with in previous sections. So I'm just going to run through this kind of quickly to hit some of the key points for you with a number of different examples. And then I'll show you basically the one or two really new things. So the first example that I want to take a look at is I want to take a look at this one where they ask you to find all 6 trig values or trig function values of a particular angle. Let's say 2 pi over 3. So in order to do this, we really want to go back to our unit circle because 2 pi over 3 is a unit circle value. And what we're going to do is we're going to use the x and y coordinates from that unit circle value to figure out our different trig values. So we have cosine of 2 pi over 3. Sorry, get the pen to cooperate here. Sine of 2 pi over 3. Tangent of 2 pi over 3. And then we have the reciprocal function. So we also have secant 2 pi over 3. Cosecant 2 pi over 3, and then cotangent of 2 pi over 3. So, my recommendation is this. If you've got the whole unit circle picture in front of you, that's great. But unless you're going to spend the first few minutes of the testing situation, the test time, actually drawing out your unit circle with all the values, that's going to be problematic, because you're not going to have that in front of you. So, whether you're going to draw the unit circle or not, my recommendation, and I've made this to you before, is to draw these very simplistic 4-quadrant pictures. So 2 pi over 3 is our 120-degree angle. Here's 2 pi over 3. The coordinates at 2 pi over 3, notice that x is smaller than y, so x gets the 1/2, y gets the rad 3 over 2, but because we're in quadrant 2, we know our x coordinate is negative. So we have negative 1/2 comma rad 3 over 2. Drawing these 2-second little pictures really makes life a lot easier. And it starts to make these coordinates and these values pop out of your head much more easily. So, remember that cosine is just the x-coordinate as long as we're dealing with the unit circle, so that's going to be our negative 1/2. Sine is our y-coordinate from the unit circle, that's rad 3 over 2. We know that tangent is y divided by x. But we don't divide by fractions, we multiply by the reciprocal, so this becomes rad 3 over 2 times negative 2 over 1, which just gives us negative square root of 3. Now, for our reciprocal values, the reciprocal of negative 1/2 is negative 2 over 1 or negative 2. The reciprocal of rad 3 over 2 is 2 over rad 3, but we have to rationalize that denominator. So we multiply top and bottom by rad 3, and we get 2 rad 3 over 3. Cotangent of 2 pi over 3 is going to be the reciprocal of tangent. So you can either make it, instead of negative rad 3 over 1, you can make it negative 1 over rad 3, or you can set it up as cosine divided by sine, x divided by y. But since we already have our tangent value, this is just going to be negative 1 over rad 3, which means we need to rationalize our denominator again. And that gives us negative square root of 3 over 3. Now, they're not always necessarily going to ask you for all 6 of the trig functions. They could just ask you for 1 or 2 of them. Maybe they ask you for tangent and cosecant. Okay, I showed you all 6 just so you see, regardless of what they ask you, it's very easy to find from the x and y coordinates. So that's evaluating the 6 trig functions for a theta value that's a real number. In this case, one with a unit circle value. If they ask you to do this with a non-unit circle value, we've talked about that before, that's where you're just going to use your calculator. And make sure your calculator is set to the proper units, either degrees or radians. Okay, the next example I want to take a look at is a problem that we have, again, seen before. If they tell you that sine of your angle t in this case is equal to 2/3, and they tell you that theta, we're using t here, t is between pi over 2 and pi, which is telling us that we are in quadrant 2. And they want us to compute cosine of t and tangent of t. Remember, I mentioned to you once before, actually multiple times before, that there are 2 different ways of going about doing this. I'm going to show you both methods to refresh your memory, and then we're going to take a look at an example where the one method becomes a little bit more problematic. So, one thing we can do is we can use our basic Pythagorean identity, cosine squared t plus sine squared t equals 1. And so we know that cosine squared t plus 2/3 squared equals 1. Cosine squared t is equal to 1 minus, I subtract this to the other side after squaring it, it becomes 4/9. So that really becomes 9/9 minus 4/9 when I get a common denominator. And so we get cosine squared t is equal to 5/9. When you square root both sides, putting in your plus or minus, you get cosine t equals plus or minus the square root of 5 over the square root of 9, which is 3. Remember, in quadrant 2, x is negative, y is positive. Therefore, this is the value that we need, negative rad 5/3. So we know that the coordinates of our points are going to be negative rad 5/3, comma 2/3. And so now we're going to do what we did on the previous one, just using the x and y coordinates. We know that cosine of t is going to be the x coordinate, which is negative rad 5/3, and we know that tangent of t is equal to sine over cosine, or y over x. So that's 2/3 divided by negative rad 5/3. That becomes 2/3 times negative 3 over rad 5. The 3's cancel, and we get negative 2 over the square root of 5. But we then have to take that and obviously rationalize it to get rid of the radical in the denominator. And so our final answer for tangent of t is negative 2 square root of 5/5. So that's one way to do this problem. The other way to do this same problem, and this is the method that I prefer, now you're welcome to use whichever one you want, but again, I like this other method because I find that it's a lot more versatile. Number one, it makes things more visual, which helps you with the positives and negatives, but also it just tends to apply to a number of different variations of this type of problem. So we're going to have the same problem, but what we're going to do now, let me just get rid of this. Instead of using our Pythagorean identity, we're going to do the triangle picture. So we're going to set up our triangle in the proper quadrant. I'm going to get rid of this for right now. So we're in quadrant 2. So here's our angle somewhere in quadrant 2. Remember, we always connect to the x-axis, never the y-axis, because in standard position, 0 degrees in radians is on the positive x-axis. So everything is measured relative to x. As long as we make adjustments for positives and negatives based on quadrant, instead of t being seen as being out here, we can treat t as if it's in the triangle. Sine is opposite over hypotenuse. Opposite and hypotenuse. Notice in quadrant 2, this one refers to our y-coordinate, so it should be positive, and it is the way we have it. There's no adjustment we need to make there. Your hypotenuse does not refer to a coordinate, so that's always going to be positive. It's strictly a length. We now have to find the x-coordinate. We're going to do that by the Pythagorean theorem. So x squared plus 2 squared equals 3 squared. X squared is equal to 9. If I subtract this to the other side after squaring it, I get 9 minus 4, which is 5. And so we get x is equal to plus or minus the square root of 5. We're in quadrant 2. So in quadrant 2, we know our x-coordinate needs to be negative. So this is going to be negative square root of 5. So make sure your positives and negatives on the x and y agree with the quadrant that you're in. That's very, very important. Okay. So now what we're going to do is we're going to find our cosine value. Well, now we're just going to use our right triangle trig. So katoa, we know cosine is equal to adjacent, which is negative square root of 5, over hypotenuse, which is 3. And notice that gives us the same answer we got with the other method. We're also going to do tangent of t. We know tangent is opposite over adjacent. Opposite over adjacent. We have to rationalize our denominator. And again, we get the same answer, negative 2 square root of 5 over 5. So this is another way of doing this problem. And again, my preference is to do it this way, because I think, number one, it's more visual, and number two, it is much more versatile in terms of what information they give us, how they give it to us, things like that. So we're going to see that on the next example. Okay. The third example I want to take a look at is the same kind of problem, but now it says if tangent of theta, we're using theta instead of t this time, is equal to 2/5, and they give us theta between pi and 3 pi over 2. And we need to compute cosine theta and cosecant theta. So cosine theta and cosecant theta. The problem with this one, guys, is when you go to plug this into cosine squared plus sine squared equals 1, you don't know either cosine squared or sine squared. We know tangent. And so that becomes problematic. And so now what you have to do is, instead of using that cosine squared plus sine squared equals 1 as your starting Pythagorean identity, you have to start with our other Pythagorean identity, which is tangent squared theta plus 1 equals secant squared theta. And from this, by plugging this in, you can solve for secant squared. From secant squared, you can get cosine. And then from cosine, you could actually work your way backwards, since we know what tangent is, to get sine. And then you have sine and cosine, you can go forward from there. That is the long way to get to where you want to go on this. And you can certainly do it. I'm not even going to demonstrate it for you up here, because I just think it's not the way that you want to go. It basically doubles the amount of effort you have to put into this problem. So what I recommend doing is, again, using the triangle method. We know that theta is between pi, which is here, and 3 pi over 2, which is here, so we know we're in quadrant 3. So we put our terminal side in quadrant 3. We connect to the x-axis to make our right triangle. Here's theta, as long as we make adjustments for positives and negatives based on quadrant. Tangent is opposite over adjacent. But because we are in quadrant 3, we know that x should be negative. We know that y should be negative. Again, the hypotenuse is never negative, because this point has these components to its coordinates. The hypotenuse is not a component of the coordinates. Okay, so what we're now going to do is we're going to use the Pythagorean theorem to find our hypotenuse. So we know that a squared plus b squared equals c squared. 25 plus 4 equals c squared. C squared equals 29, so c is going to be plus or minus the square root of 29. Since it's the hypotenuse, it cannot be negative. It's got to be positive no matter what quadrant you're in. And you get this value for your hypotenuse. Now that we have all three sides, it's very simple to use our right triangle trig to evaluate cosine of theta, which is adjacent over hypotenuse, negative 5 over the square root of 29. You rationalize your denominator to get rid of the radical on the bottom, and you get negative 5 square root of 29 over 29. Clean, simple, and quick. Cosecant of theta. Cosecant is the reciprocal of sine. Since sine is opposite over hypotenuse, cosecant is going to be hypotenuse over opposite, which I would just rewrite as negative square root of 29 over 2. So again, the triangle method, in my opinion, is far superior to using the Pythagorean identities. It's quicker, it's cleaner, it's less confusing, and it's very visual. Okay, that brings us to example number 4, and the fourth example that I'm going to show you is one that you have not seen before. These are problems where they're going to give you an expression. So in the expression, u over the square root of u squared minus 1, they give this to you. They tell you to make a substitution. So make the substitution u is equal to secant theta. So what they want you to do is they want you to plug secant theta in place of the u's, and what they want you to do is to show it simplifies to cosecant theta. And they tell you to assume that theta is between 0 and pi over 2. So they're just telling you theta is in quadrant 1. In other words, they're simplifying this so that we don't have to worry about any positives or negatives getting in the way, which is nice. That's just them making the problem easier, not harder. Okay, first thing we're going to do is we're going to substitute. We're substituting, so we need to use parentheses. This becomes secant of theta in the numerator over the square root of secant of theta quantity squared minus 1. So what this gives you is it gives you secant theta over the square root of secant squared theta minus 1. Remember that if they give you a number here like 2 secant theta, you have to square the number also, and it would give you 4 secant squared theta, not 2 secant squared theta, so be careful with that. Now this is a very simple version of these problems, just to show you the basics. You'll see some slightly more complicated ones on the assignment. But what's always going to happen at this point is the stuff inside of the radical will allow you to make a Pythagorean substitution. Now sometimes, for example, if this was a 4 and this was a 4, what you'd have to do is you would have to pull the 4 out, not out of the radical. It would just come out to the front, and then you would get your secant squared theta minus 1. So be on the lookout for that. This one does not have that particular issue. Again, I'm trying to keep this example simple so you can get the basic idea. And then we can work through the harder ones in class if you have any trouble with it. We know that tangent squared theta plus 1 equals secant squared theta. If I subtract 1 from both sides, I get tangent squared theta is equal to secant squared theta minus 1. That means I can take the secant squared minus 1 out, and in its place, I can put, still inside the radical, tangent squared theta. You're always going to be able to make one of these substitutions. That's the nature of these problems. If you're not able to make one of those substitutions and then be able to simplify this radical easily, you're not doing it right. You're making the problem too difficult. We now have to take the square root of tangent squared. Well, the square root of tangent squared is obviously going to be just tangent of theta. And so now we have simplified this thing down to secant theta divided by tangent theta. Now this becomes one of our trig expression simplifying problems. I'm going to now change these things into sines and cosines. So secant is 1 over cosine theta divided by tangent, which is sine theta over cosine theta. We don't divide by fractions. We multiply by the reciprocal of the denominator. When you do that, this just becomes 1 over sine theta, which we know is cosecant theta. Now, how did I know to keep going from 1 over sine theta to cosecant theta? They told us to show that it simplifies down to that. If they did not tell us to show that it simplifies down to anything in particular, if they just told us to simplify, then we could have stopped at either one of these two answers because they're both involving simply one trig function. Now, personally, I like the one on the right better because it's a little cleaner looking, but there's nothing wrong with 1 over sine theta if they didn't specify what we're aiming for. Because truth is, if you wanted to punch it into your calculator, if they asked you to evaluate it for a particular angle theta, you can't punch cosecant directly into your calculator anyway. You'd have to punch it in as 1 over or 1 divided by sine of theta because we don't have a cosecant theta button. All right, so that's our fourth example. One more example, and then we'll call it quits for this section. The fifth example I want to show you really involves what we call opposite angle identities. And the opposite angle identities tell you what happens when you have cosine of negative theta. So cosine of negative 30 degrees, cosine of negative 5 pi over 4. And it turns out that with the cosine function, cosine of negative theta, the negative disappears and it just becomes the same thing as cosine of theta. So for example, cosine of negative 30 degrees gives you the same thing as cosine of positive 30 degrees. If we think about that, positive 30 is here at rad 3 over 2, comma 1/2. Negative 30 is here at rad 3 over 2, comma negative 1/2. Notice that what the negative angle to positive angle is doing, guys, is it's flipping us over the x-axis. And whether you're flipping between quadrant 1 and 4, or whether you're flipping between quadrant 2 and quadrant 3, notice that your cosine, your x-coordinate, is the same in both of those two reflected quadrants. If you're dealing with quadrants 1 and 4, cosine is positive in both. If you're dealing with quadrant 2 and quadrant 3, cosine is negative in both. And so the sign stays the same. And so that's the way this works for cosine. This is positive rad 3 over 2. This is positive rad 3 over 2. If we were over here, we would get negative rad 3 over 2 and negative rad 3 over 2. So the reflection doesn't change anything. We get the same value. That's the idea. So if you ever run into this, cosine negative theta, in a trig proof or something, you can take it out thanks to this identity, and you can substitute in cosine of positive theta. And then you can move forward from there. Now, sine of negative theta and tangent of negative theta do not work the same way. Again, it's a reflection over the x-axis. But if you look at sine, notice that sine of 30 is 1/2, sine of negative 30 is negative 1/2, because sine is positive in quadrant 1, negative in quadrant 4. The sign, S-I-G-N sign, changes when you reflect over the x-axis. Same thing here. Sine is positive here, negative here. So it turns out that you can change this to sine of theta, but the negative comes out to the front and you get negative sine of theta. So in other words, cosine of negative 30 degrees, sorry, we're dealing with sine now, sine of negative 30 degrees is equal to negative sine of positive 30 degrees. This is negative 1/2, this is 1/2, that's why the negative has to get glued on manually in the front. Now, because tangent is sine divided by cosine, obviously we're going to get, in this case of our example, negative 30 degrees divided by, negative sine of 30 divided by cosine of 30. We're going to get a new negative introduced, and so again, just like sine, tangent requires that that negative be brought out front. So this is the way the negative angle identities work, or the opposite angle identities, I should say. Notice that because cosine just loses that negative, secant will do the same thing. It's just the reciprocal of cosine. So secant of negative theta is the same thing as secant of theta. Because sine and tangent change from positive to negative or negative to positive, then cosecant and cotangent will do the same. And so that's the way the opposite angle identities work, and those are usually going to pop up, like I said, somewhat in evaluation problems, but also in trig proofs and simplifying trig expressions, things like that. Okay, so that is lesson 7.1. Do not forget, if necessary, go back and rewind and watch the parts again that didn't sink in. Also, do not forget that you guys need to take notes on the section. I want to see notes when you come into the class so that I see that you are actually watching it. And in addition to that, I would like you to write down a minimum of one question that you would like to ask me. And you could ask it when I come around while you guys are working. That question could either be something that doesn't make sense to you, that you're struggling with trying to comprehend and you need some clarification. It could be a question on a particular problem, because you're welcome to go online and look at the calendar and see what the assignment is and go ahead and start on that if you'd like. You don't have to, but I would recommend that you at least go through and try and do the easy ones so that we can spend our time in class tomorrow going over the more complicated ones, the ones that really give you trouble. But you could certainly ask questions about that. The other thing that you can do, which I have no issue with whatsoever, I actually encourage it, is maybe you have a thought about, how this might apply to something else in the real world or in another class. So if you have a deeper kind of question where you have a what if, or how is this used, or something like that, that could qualify as your question as well. Okay, I want you guys to think beyond the problems that are on the page whenever possible. So it's up to you. There is no maximum number of questions you can write down. I would like you guys to write down a minimum of one, just so I can see what issues that you're having when I come around and talk to you in class. Okay, that is the first video in our flipped classroom model. Thank you for watching that, and I will see you guys tomorrow.